Is there?
What did you have?
Yeah, I'm looking for the pointer.
Go
Okay.
and just to check the microphone, can you sit?
Yeah. Do you hear me? Yeah. All right. Okay. So yes, indeed, I'm telling you about the work I'm doing for the use of formal methods for the verification of quantum programs. I'm working in Université Paris-Saclay, and the lab is called LRE. So the starting idea is that quantum computers are going to arrive and be available for programmation in a future that we expect to be a near future. And so our question is how to write programs for these computers that we know to be correct programs with regards to our specifications and our requirements from these programs. So to tackle this question, we need specification and verification mechanisms, and we have a set of specifications for these mechanisms. We want them to be scale invariant, to be able to verify quantum programs of any size. We want them to enable programming that looks like the descriptions of the algorithms from the literature. We want to be able easily and automatically to distinguish the effective program from its specification part, and we want it to be to enable proofs in a manner that is automated as far as possible. So for all this, we are developing a core building circuit language that is called Kubrick's, and that comes with some semantical means that are some means to interpret the terms of the language as mathematical objects. And this enables to introduce high-level specification framework and verification of their specifications. And thanks to that, I could implement a certified parameterized version of the phase estimation algorithm as a case study. So I will first give a general word about the use of formal methods in quantum computing, then present briefly my contribution, Kubrick's, and say a word about the case study. So first, basically, the state of affairs in quantum computing is such that we have a series of quantum algorithms that have been described in the literature. So here is just a screenshot of the phase estimation from Nielsen and Chang manual. So we have these algorithms. We have a series of quantum programming languages for implementing these algorithms, and these languages works by building quantum circuits. And so the question is whether the circuits that are built by a program aiming at implementing a given algorithm, whether this circuit is indeed a run of this algorithm. So the question is very common in computer science, but it is a bit particular in the context of quantum computing for several reasons. So it has been evoked also this morning. Maybe the first thing is that quantum programming is particularly tricky and unintuitive, and I put this warning of Richard Feldman, saying that if you think you understand something there, it means you didn't understand anything. I don't know if you can read the quote, but this is what it is saying. So first reason, one has to care about his intuition of what the program does, and two other reasons that are more objective and more directly linked with the very nature of quantum computing. The first one is that the basic strategy of inserting in the execution of the code some tests for, say, the values of given variables, and then we start the execution. This strategy is not applicable because of the destructive measurement. And another strategy based on test would consist in testing whole executions and test the outcome. And this is hard also to handle because of the non-deterministic nature of the calculus. So to apply such a strategy, one would have to test a statistical distribution, and so to run a set of tests large enough to rebuild a statistical distribution. So our conclusion is that any strategy that is based on testing is difficult to handle, not to say impossible. And so we ask, what about full verification? Because such a strategy would bring solutions to the dead ends of testing strategies. And in addition, it would allow to handle infinite state or unbounded state spaces. And it would also enable to provide once for all absolute guarantees of the correctness of a program. So this is what we are doing. Now, if we come back to what is a quantum algorithm, what are the algorithms that we want to implement and to verify. So here I we put the phase estimation from Nissan and Schwang again, and I just want to have a look at the very structure of this description of the algorithm, the way it is presented. So we have two columns. On the right-hand side, there is a sequence of operations that are declared. So initialize the state, create superposition, apply black box, and so on. And in parallel, on the left-hand side, we have a series of intermediate assertions, which are formal descriptions of the state of the system and of its evolution along the performance of the operations that are on the right. And so this very specific format is very interesting for us because we can interpret it directly as contracts for the implementation of this algorithm. So for example, here, the function create superposition. We can interpret the element from the left columns as contracts saying that, okay, you can implement the function create superposition in any way, provided that if the input of the function satisfy this blue condition that we call a precondition, then you ensure that the output will satisfy the red expression, that is a postcondition. And so we can write it in this kind of manner with declarations of functions, their implementation, and in the very code, decorations with pre- and post-conditions of the functions that we are writing. So this is called deductive verifications. Then the compilation generates proof obligations that we have to fulfill. So we made the choice to embed our work in the Y3 environment that enables such programming in deductive verification, and which is based on the OCaml language. So concretely, we are building quantum circuits. So what is a quantum circuit? We take it very simply as an algebraic object. So a quantum circuit is a set of objects, blue boxes here, that are assembled together either in parallel, like here, or in sequence. And each of the blue boxes is itself a quantum circuit that is an assemblage in sequence or parallel of smaller circuits. So a very simple algebraic structure with a set of primitives that are the elementary gates of the calculus. So here the phase gate, the rotations, and the control knot. And then two relations of compositions of circuits in sequence and in parallel. So we are relying on this algebraic type to define circuits. And now we want to specify these circuits. So to do so, we need a formal interpretation of these circuits. So they are functions transforming quantum states into quantum states. And we need a semantics to describe these functions. So I choose to use the Passam semantics that was proposed by Matthew and me 2 years ago. And what it says basically is that for any quantum circuit, for any state of the computational basis, applying this circuit to these states results in a state that has this general normal form. And this general normal form is a sum of elements, each of them being a complex scalar coefficient times a vector of the computational basis. So the thing is that to completely describe the action of a given circuit over any quantum state, we need basically three main elements, which are in red here the range of the sum, then the function in blue identifying the scalar complex coefficient, and this green function identifying elements of the computational basis. And the interesting thing is that each of these three different elements, so the red, the blue, and the green, has a definition that is recursive over the algebraic structure of circuits. So to use it, we are going to use these three functions, the red, the blue, and the green, to specify the circuits that we are building. So the first step here, it's very schematic, but the first step was to define what I call lifted constructors that are functions simulating the algebraic constructors and coming with specifications in terms of the semantical function. So parallel comes with post-conditions in terms of the red function, of the blue function, and on the green function. And I prove the correction of the specification in a logical context that is the mathematical theory supporting the specification language. Now that I have these lifted constructors, I can use them to build a quantum circuit. So here I have, for example, circuit B. It comes also with three post-conditions, a red, a blue, and a green, that is proved correct in the same logical context. And the interesting thing is that, and it is the way Y3 compiles the specifications, when I define a composed circuit, so here a parallel composition of B and C, to support the specifications of this composed circuit, I can, I have integrated in the logical context the post-condition, the specifications for its element and for the constructor that is used in this composition. So basically, there is a kind of mapping isomorphism between the algebraic structure of the circuits that I'm building and the branching structure of the proofs for their specifications. So this is the main feature that I'm using and taking profit on for the specification and the verification in Kubrick's. Now I also started working on getting further automation of the proof support. This has two directions. The first one is to take profit on some nice properties of the semantics, like it is linear, it translates sequence as function compositions, and so on. So to take profit on these properties, to introduce and work with more abstract specifications. And like the main example here is eigenvalue specifications that was helpful for the implementation of my case study, the phase estimation. One thing is that having such abstract specifications and being able to reason on it is very, very important when we are dealing with real quantum algorithms, where in the general case you often have as a parameter a circuit that is not completely known, but that is just given with such an abstract specification. So I started implementing the tools to reason with it. This is the first direction, and the second direction was simply to identify fragments of the language, subclasses of quantum circuits, for which there is a simplified version of the path-frame semantics. And so here, two of such fragments, what I call flat and diagonal fragments, with the type of the semantics that is simplified. One word about the case study implementation. So it is the phase estimation algorithm, a parameterized version. These are data about the implementation itself. Maybe don't worry about the first lines. It corresponds to a partition of the implementation. But just see that the overall implementation is 237 lines long, including the specifications. It generates 190 proof obligations. 24 of them are not automatically verified by SMT solvers. And to finish their proof, I had to enter manually 163 transformation commands so as to ease the proof fulfillment. So to conclusion, it's possible to apply formal verification in quantum programming with real algorithms, but there is still place for some further work toward further automation. And so the second table aims at evaluating the first efforts that I made in this direction. So I took a part of the implementation that is the quantum Fourier transform. And I implemented several versions of it, differing on the semantical tools that I used for the specifications. So one with full kubrics, one with only pass sum. I mean not using the simplified version of pass sum semantics for the good fragments of the language, and one with matrix semantics. And if we just look at the number of interactive commands that I had to enter to completely finish the proof, what we can see is that using pass sum instead of matrix gains a factor 2 improvement. And then by refining pass sum, I gained another 40% in terms of these interactive commands. So in conclusion, very briefly, so I have a core development fragment for certified quantum programming, enabling scale invariant specification and verification, in which we can program in a way that is directly derived from the description of algorithm in the literature, which can distinguish automatically the effective part of the code from its specification, and which I work for being more and more automated. So basically, the implementation, there is this circuit building language, two semantics, the pass sum and also the matrix semantics, plus the equivalence proof between them, some shortcuts for further automation, and this case study that is the phase estimation algorithm. In future works, there are many different directions. Here, two of them: further automate the proof fulfillment and extend the language to the management of to the classical control flow, and that will come with an extension of the case study to the Shor algorithm. And I thank you for your attention.
Okay, there seems to be a question over there.
Hello, nice talk. So I have several questions. The first one is that I guess what you verified is like quantum phase estimation really, like your implementation is faithful to the quantum phase estimation. So, but it's well known that quantum phase estimation is an approximation, you know, like to some digits. So I it's surprising that you didn't mention anything about like you really estimate some phase. So.
Sorry?
So like the phase estimation claim, what it claims is that
you're right. I answer this one first, or
I'm sorry.
You have another question actually.
Yeah.
I'll answer this one first. Yes, indeed. Actually, at the present state of affairs, it is phase estimation in case the eigenvalue is dyadic, and it can be written by a dyadic fraction of length a given integer.
So you consider the approximation already?
Yeah. But I'm working on it, so it's a matter of time, and there is no particular obstacle. But now I consider that as an input, that the unitary operator I'm searching the eigenvalue of, that this eigenvalue, if of type k over 2 to the power of n, where I fix my n.
Oh, I see. Okay. Yeah. And another question is that so in the maybe in the quantum textbook or like in the original paper of quantum phase estimation, there already is a manual proof, like kind of like maybe recursive or like inductive proof. So here you use the path polynomial approach. So what's like, and it's scale invariant. So why do you choose another approach to prove it, like comparing to the inductive one or the original one? And what's the advantage, or why do you choose to use it?
I must admit I didn't see the original proof. But anyway, what I want, phase estimation is an illustration. It was just to give a proof by the fact that it's possible to apply formal verification to quantum computing. What I was looking for was a general formalism to specify any quantum circuit and any quantum circuit construction. So this is what I was looking for.
Okay, I see. Okay.
So you have
Hi, I'm Yuxiang from Maryland, and have some questions for you. So first thing, you claim that the cubrics are scale invariant, but I can't find that you put scales in your specifications or any maybe data structures like quantum circuit.
Yeah. The circuit for phase estimation is defined with a parameter that is an integer, and that with a parameter that is the circuit we are looking for, we are searching the eigenvalue of, and the size of this circuit is not bounded. The proof that I wrote works for any such circuit of any size.
So
Does it answer your point? Or?
So it's not a theorem like for all input lengths, it always correct.
Yeah, it has this. The final result is of this kind. Yeah.
Maybe we can take further questions offline, because otherwise unless there's some very quick question. Okay, then let's thank the speaker again.